Welcome back, everybody. We've got just a little bit of sunlight here we're going to be fighting with, but I think we'll make it work. We're going to continue on talking about the second law, talking about entropy. We've introduced the second law, and we've derived it down for a process from state 1 to state 2. So, again, just a generic differential form of the second law. Looks like this. We say the change in entropy is going to be greater than or equal to an amount of heat transfer that causes that entropy change divided by the temperature at which the heat transfer occurs. And this differential form's nice. It's always true. And we've not had differential equations and not expecting you to have an in-depth understanding of how to apply differential equations or solve them. And this is a differential inequality on top of that. What we normally do is we convert this to an algebraic expression that we can use, and we say, well, for a process from state 1 to 2, the entropy change, total entropy change, is going to equal what happens if we add up all of the heat transfer from state 1 to state 2, all the heat transfer per unit temperature. And again, the second law says that this entropy change has to be greater than this quantity. And what we do is we say, well, let's just add the amount by which it is greater. That is the entropy that has been generated. Right? And that's where we say that entropy generated has to be positive. We cannot destroy entropy. Negative, if the entropy generated is negative, that would indicate we have destroyed entropy. And to the best of our knowledge, that is impossible. Now, if you divide by mass, it's the same expression. It's just everything is now lowercase. Everything is an intensive property. Where this is extensive, this depends on how large, how much mass we're dealing with. This does not. Or we could work per unit time. We said, hey, take m dot times then these mass-specific s's, the little s's, and that's going to equal the total rate at which heat has been transferred to the system per unit temperature, plus the rate at which entropy is being generated. In all three cases, we cannot destroy entropy. The entropy generated must be positive. And so that's just kind of a quick review there. Now, we talked a little bit about this entropy generated, and we said that entropy generation has to be positive. Okay, that's the rule. We cannot destroy entropy. And we just we kind of got right up to starting to talk maybe about isotropic situations or isotropic situations. Iso referring to constant, entropic referring to entropy. So that just tells us that if the entropy is constant, that means we're not changing the entropy. So there's two ways we can change the entropy. If we can avoid both of those, then it's isotropic. But there's two ways we can change the entropy of our system. One is we can add heat, or we can remove heat. In either cases, that's going to change the entropy of our system by either adding or removing heat. The other one is what we call irreversibilities, and that can take a number of forms. It can be friction, it can be a lot of chemical reactions are irreversible. Most chemical reactions will generate some entropy. Some of them can generate a lot. If you burn a hydrocarbon, you're generating lots of entropy by doing that. So this entropy exchange via heat transfer, that is this guy, this integral dq over t. This is this one. Irreversibilities, that is where we have generated entropy. We've done something, there's now more entropy in the universe. We cannot go back to the original state, right? Because again, the entropy generated accounts for not only the entropy increase in our system, it also accounts for the entropy increase in the rest of the universe. So it's the total entropy that is now generated. We cannot go back to the initial state for the system and the surroundings. So that's irreversible. We can't go back. And to the best of our knowledge, everything we do is irreversible. Everything we do is always generating entropy. That's kind of the whole crux of the second law. But that's how we quantify these two. And you can see that when we look at the second law as we've applied it to a process from state 1 to 2. We're saying, look, if I'm changing the entropy, it's going to take one of two forms, either heat transfer or irreversibility. Okay. So what happens then is if you have Q equals 0, and we call this adiabatic, and it's reversible. Right? So if it's adiabatic, that means there's no heat transfer. And if it's reversible, there's no entropy generated, meaning S2 minus S1 is equal to, again, this integral Q over T plus S gen, and we're saying both of these go to 0. So the entropy change is 0. Okay? This is what we call isentropic. Okay? Isentropic means it's adiabatic and reversible. It has to be both. It has to be both. Now, in the craziest situation, you could have this be negative, where the system's losing heat. That's actually not that crazy. You could have the system losing heat, so this is a negative quantity, while it generates an equal and opposite amount of entropy. Right? So these two could add up to be 0, and you still have an isentropic situation. So I always like to draw this as an arrow. It's kind of a caution here that adiabatic and reversible, you put those two together, but I always put an arrow on this. If you have these two, you know it's isentropic. If you know it's isentropic, you don't necessarily know that these are both true. Right? Again, this can be 0 if this is negative and this is equal and opposite this amount. If these two add up to be 0, then it's still isentropic. Just because you know it's isentropic does not mean it's adiabatic and reversible. But if you know it's adiabatic and reversible, you know it's isentropic. This goes one way, not both. Okay? Just be aware of that. I used to say I wouldn't put that on a test, and then one time I just kind of inadvertently, without even thinking about it, put a simple common household object. I put a cell phone charger. A cell phone charger. You can easily show where that would be kind of an isentropic situation, even though it's generating entropy. I digress. So I always draw an arrow here. If you know these are 0, if you know there's no heat transfer and it's reversible, then you know it's isentropic. If you know it's isentropic, you don't necessarily know that both of these are 0. If I know it's isentropic and it's reversible, then I do know it's adiabatic. So if I know 2 of these are 0, then I know the third one has to be 0. I'm comfortable with that statement. And if you know 2 of those are true, then the third one has to be true. Okay. All right. So, again, how do we know this? Well, or what does that show up like in a problem? Our text likes to use, they'll either tell you it's adiabatic, they'll tell you it's well insulated, they'll tell you it's negligible heat transfer. That's how our text will tell us. that it's there's no heat transfer. The reversible process. How do you know that it's a reversible process? Well, they'll tell you that maybe there's no friction, but the common thing that a lot of thermotechs will tell you is they'll tell you a maximum output. Right? Or maybe it might say minimum input. I'm going to write this on the paper. I'm going to get a much better result if I put that on paper. Hang on here. Right. So common ways that a textbook would tell us, how do we know if it's reversible? Well, it's the best, the biggest thing you have to understand is the problem statement will somehow communicate to you that this is the best version of the device. If the problem statement is somehow communicated to you that you're dealing with the best version of the device, then that means that it's reversible. How does that show up? Well, again, as I said, that's like for a turbine, we want a turbine that generates the maximum output. We want a turbine to generate the most output, the most power output. If it's a compressor, it's going to be the minimum input. If it's a nozzle, it might be the maximum exit velocity. If it's a diffuser, it might be the maximum exit pressure. It depends on what is the purpose of the device. Don't just get stuck on the max and min, because if I say, well, determine the compressor that requires the maximum input, well, that doesn't make any sense, right? The compressor that requires the maximum input is a compressor that doesn't do anything. It just spins. What is the purpose of the device? Right? What is the purpose of the device? And if it's reversible, it will achieve or provide the best possible result based on that purpose. That's how you know if it's reversible. And the common thing, it's kind of a giveaway if the problem statement says determine the maximum something. That's kind of a giveaway, but you really want to stop and think and say, what is the purpose of the device? And does that maximum actually tell me anything useful? And most of the time it will. That's not the kind of thing that we're going to mess around too much with. Okay? All right, so I've got an example here that's, rather than dive into the example and have to stop here in a second, let's stop there, break the video up, and we'll start up on this example with the next video. Okay, so loud pop.